Hello, my name is Abdullah Zaid, and I will present to you my thesis work on urban air mobility communications, area-terrestrial heterogeneous networks. How many of us have experienced the frustration of being stuck in traffic? Every year, the average person spends hundreds of hours in congestion, wasting valuable time. And this problem is only getting worse. By 2015, nearly 70% of the world's population will live in urban areas. Hence, we look to the skies. Urban air mobility, or UAM, represents a new approach to transportation, which uses advanced technology such as electric vertical takeoff and landing vehicles. UAM will offer the potential to bypass ground congestion, reduce travel time significantly, all the while using sustainable modes of transportation. However, eVTOLs will require constant connectivity for navigation, traffic management, and safety. Hence, for UAM to be safe and efficient, a strong communication infrastructure is essential. We can use existing infrastructure such as cellular towers, however they have limited coverage and limited line of sight capabilities. We can also use non-terrestrial networks which have higher coverage and clear line of sight links, however they are sensitive to weather and have limited capacity. Hence, we propose a heterogeneous network that integrates both cellular towers and aerial base stations, combining the strengths of both for more reliable and scalable UAM communications. To assess the feasibility of the SetNet communication infrastructure, a coverage analysis study is important to identify coverage gaps, optimize network infrastructure, and predict and mitigate interference. Our system model defines processes that realistically capture the eVTOL distribution, the aerial base station distribution, and the terrestrial base station distribution. Now, we assume that the eVTOLs attempt to associate to the base station providing the maximum average power. Our system model identifies three possibilities: connecting to an aerial base station, terrestrial base station in line of sight, or terrestrial base station in non-line of sight. We also assume that the connection is made for both uplink and downlink, which we call the coupled association. However, instead of just picking the strongest signal, we add bias factors to adjust which base stations eVTOLs connect to, helping balance the load and improve performance. Now, we define the joint uplink and downlink coverage probability, which is the probability that both the uplink and downlink signal to interference ratio exceed a threshold at the same time. We define the SIR in the uplink to be the main link power divided by the interference power received from other eVTOLs, while we define the downlink SIR to be the main link power divided by the interference received from other base stations. Now we show the results of the coverage probability as a function of the bias ratios, where all the way to the left it's fully associated with the terrestrial base station, and all the way to the right fully associated with the aerial base station. We see for the performance that the aerial base station outperforms the terrestrial base station by themselves, but if we use a heterogeneous network, we see an 11% increase in improvement over the aerial base station. However, what if we decouple the uplink and downlink? In other words, allow the eVTOLs to connect to different base stations in uplink and in downlink. In our 3 base station type model, this means that now we have 9 different possibilities for the decoupled association. The association expressions are now unique as well for uplink and downlink, while introducing different biases for each case as well. Now, if we see the decoupled performance compared to the coupled performance, we see that we have a 19% increase over the coupled coverage probability. In conclusion, we proposed a heterogeneous network for urban air mobility. We showed that the aerial-terrestrial HETNet outperforms the aerial only by 11%, and that the decoupling outperforms the coupling by 19%. Thank you.